All right. So today we have Reuven Hodges from UIUC, and he's going to talk about Coxeter combinatorics and spherical Schubert geometry.
All right, thank you. So thank you for everyone showing up. And yeah, so everything I'll talk about today is joint work with Alex Yong here at UIUC. And so yeah, let's dive right in. Let's start off talking about Coxeter combinatorics first. So just a bit of definitions and background to start with. So notation-wise, for a positive integer r, when I write bracket r throughout the talk, it will always be the set of integers from 1 to r. And so now just a bit of background, a Coxeter diagram is just a simple graph with nodes labeled by 1 through r and edges labeled by integers greater than or equal to 3 and infinity. And so given a Coxeter diagram, there is an associated Coxeter group. This is defined by being generated by simple reflections S1 through SR with relations given by the diagram. In particular, the square of any simple reflection is 1. Two simple reflections commute with each other if they are not adjacent in the diagram. And then you have these braid-like relations that have Mij generators on each side if the edges I and j are connected by an edge labeled by Mij less than infinity. And just as a bit of convention, the edge labels that are equal to 3 are usually omitted from the graph. So just as a quick example, the A3 Coxeter diagram looks like this. It's 3 nodes connected by 2 edges, and the associated Coxeter group to this Coxeter diagram is the symmetric group S4, right? S4 has 3 generators, they all square to 1. And for example, S1 and S3 commute with each other because they're not adjacent in this graph, etc. And so you can check that these relations that I list up here exactly give you the relations that generate S4. Okay, so this is Coxeter diagrams and Coxeter groups. Now just a bit of terminology associated with all of this. So if you have an element inside of Coxeter group, then the length of this element is just the minimum number of generators required to express that element as a product of simple reflections. And then a reduced expression of W is just some ordered product of minimal length that is equal to W. Okay, and so a Coxeter element is, so an element is a Coxeter element if it equals the product of all of the generators in your Coxeter group in some order, right? So for example, S4 has 3 generators, and so S2, S1, S3 is an example of a Coxeter element, okay? All right, so now parabolic subgroups. So take some subset I in bracket R. We have an associated parabolic subgroup of W that we'll denote by W sub I. And this is just the subgroup generated by the simple reflections Si, I, and I. Okay, so this is some distinguished subgroups of the larger Coxeter group. And so kind of lemma that's sort of trivial and immediate by the definition, but is actually kind of important throughout this talk is the following. Just an element is a Coxeter element in some parabolic subgroup if and only if each simple reflection appears at most once in any reduced expression. So just as a quick example, for this same W equals S4, W is generated by this S1, S2, S3. So for example, S3, S1 is a Coxeter element in some parabolic subgroup, but S2, S1, S2 is not because S2 appears twice in the reduced expression. Okay, so being a Coxeter element in a parabolic subgroup is equivalent to all the simple reflections appearing at most once. Okay. All right, so just a little bit more terminology. So if you take a subset I of bracket R again, you have an associated induced subgraph G sub I. So what you do is you just take the induced subgraph on those nodes. And if you take an induced subgraph, this induced subgraph is going to break into connected components, some number of them. There might be 1, there might be more. I'll label these connected components by these C superscript Z's. And then associated to each of these connected components, there is some parabolic subgroup and there is some longest element in that parabolic subgroup. So just as a quick example, you take the E8 Coxeter diagram, and let's say my I is going to be the set of nodes 2, 3, 4, 5, 7, and 8. So if I take the induced subgraph that you get from E8 on these nodes, you get 2 connected components. You get this 4-node connected component and this 2-node connected component. And the associated Coxeter groups that you get, well, associated to this first connected component, you get a D4, and associated to this second one, you get an A2. And then these are the respective longest elements in each of these 2 Coxeter groups. Okay. All right, so I think that's all the background material that we need. And so now I can give you kind of the central definition of this talk. Well, not this definition, but right after this definition, I'll give you the central definition. So just a descent set. So you take some element in your Coxeter group. The descent set is the set of all nodes such that when you multiply W on the left by the associated simple reflection, it decreases in length. Okay, so this is the descent set of W. And so now we can actually do the main definition. And it's a little bit complicated, and so we'll work through this pretty carefully. So the pieces of data that you start off with are, you start off with some element in your Coxeter group, and you take some subset of the descent set. So this is just some subset of nodes. And then associated to this subset, you also have an associated induced subdiagram with a bunch of connected components. So these are the piece of data that you start with, is an element, a subset, and an induced subgraph. And then we'll say that W is I-spherical if there exists a reduced expression of W that satisfies 2 conditions, okay? So the first condition says something about certain simple reflections should appear at most once. In fact, any simple reflection that does not appear in I should appear at most once. And then the second condition is a little bit more complicated. It's saying that certain simple reflections associated to a particular connected component should appear not too much, is basically what it's saying. So it'll be much clearer with an example. So we'll work through a couple examples here to make this clear, but that's the basic idea, is that certain simple reflections should appear at most once. Other ones can appear more often, but not too often. All right, so let's just do like the kind of trivial example. So here we'll take any W and we'll take I equal to empty set, okay? So if you take the induced subgraph that you get from the empty set, well, you just get nothing. So you have no connected components. So in particular, the S2 condition just becomes vacuous, right? There's no connected components, so there's no S2 condition. What does the S1 condition become? Well, the S1 condition becomes, well, all the simple reflections that are not in I should appear at most once, but all of them are not in I. So all of your simple reflections should appear at most once. So by lemma 1, right, we have that then given a W in our Coxeter group, it should be empty set spherical if and only if it's a Coxeter element in a parabolic subgroup, because this is equivalent by the lemma to each simple reflection appearing at most once. Okay, and so this is the sense in which this definition of spherical elements is a generalization of Coxeter elements, right? When I is the empty set, it really is genuinely just saying it should be a Coxeter element, or at least a Coxeter element in some parabolic subgroup. And what's going to happen now is, well, we're going to make I larger. And what's going to happen is, well, now some simple reflections can appear more than once, but they can't appear too often. Okay, so that's the idea, or the sense in which this is a generalization of Coxeter elements. Okay, so let's look at a more complicated example now. So we'll look at this same E8 Coxeter diagram. And let's start off with W being this very long word. And so I'm going to tell you that the descent set of this W is 2, 3, 4, 5, 7, 8. And I'm going to just take my I in this case to just be that full descent set. So I'm going to take I as large as possible. And as we saw in the previous example, when you look at the induced subdiagram that you get associated to this particular choice of I, you get two connected components, right? You get this C1 connected component and this C2 connected component. So now what we're going to try and do is we're going to try and see, does this particular reduced expression for W satisfy condition S1 and S2? That is it I spherical for this particular choice of I? Okay. All right. So we'll first look at this S1 condition. So the S1 condition says all the numbers that do not appear in here, that do not appear in JW, those simple reflections should appear at most once. So 1 doesn't appear, so S1 should appear at most once, and it does, it appears exactly once. 6 is not in here, so S6 should appear at most once in here, and then you can check, and indeed S6 appears exactly once, and so condition S1 is satisfied. Now we go through for condition S2 for each connected component. So we'll do it first for this larger connected component, that's nodes 2, 3, 4, and 5. In particular, what you want to do is you want to count the number of times that S2, S3, S4, and S5 appear in this reduced expression. That's 12 times. And you want to check and see whether that is upper bounded by the length of the longest element inside of the associated Coxeter group. That is the longest element in D4, plus the number of vertices. Well, the longest element in D4 is 12, and the number of vertices is 4, and 12 is indeed less than 16. So this satisfies S2 for this particular connected component. And then the final thing we need to check is now S2 for the second connected component. And so you count the number of times S7 and S8 appear. They appear 5 times. And then you just check, well, the longest word in A2 is length 3. The number of vertices in A2 is 2. 5 is less than or equal to 5. And so S2 is satisfied for the second connected component. So it turns out that this W is I spherical for this particular choice of I. Now, there's a couple things to say at this point. I sort of chose the reduced word in such a way that this would work out. If I'd chosen different reduced words for W, this might not have worked out. But the whole point is, right, there exists a reduced expression. So you need to only find a single reduced expression that satisfies both of these conditions at the same time, okay? All right, so that is the main definition, the main combinatorial definition at least. And at this point, it maybe seems a little unmotivated in the sense that I've given you sort of something that's maybe a generalization of a Coxeter element, but what is there more motivation behind it? And there is indeed geometric motivation behind this definition. And so that's what I'd like to talk about now, as long as there are no questions. Okay. All right, so I'll now talk about some of the geometric motivation behind this idea, and then I will talk about how you connect the geometric notion to this combinatorial notion. Okay, and so to do that, I'd like to talk about 2 topics in combinatorial algebraic geometry. And so the first one is kind of near and dear to my heart. It's flag varieties. And so a flag is just a nested sequence of vector subspaces, F1 sitting inside of F2, et cetera, inside of C to the N. And we say that this flag is complete if it satisfies 2 conditions. You would like that the dimension of the flag Fi is equal to I, and you would like that there are N of these. So if that's true, then this is called a complete flag. And so if we take GLN to just be the general linear group of n by n invertible matrices with entries in C, and we take B to be the subgroup of upper triangular matrices, then if you take a coset GB, that coset GB is determined by the following set of subspaces. What you do is you take the first column vector of your matrix G, and you think about the span of that. That gives you some line. If you take the first 2 column vectors, and you think about the span of those first 2 column vectors, that gives you a plane. And in fact, your line is sitting inside of the plane. If you take the first 3, you have a 3-dimensional subspace that contains the plane, that contains the line. So this is in fact exactly giving you a flag associated to this coset. And in fact, it's more than that. This actually gives you a bijection between the cosets in GLN mod B and the complete flags. And so this is why GLN mod B is often called the complete flag variety. And so you can put a variety structure on this, or there is a variety structure on this set of complete flags. And so, okay, at this point you have this complete flag. So one thing you might think about is actions on this complete flag. And so there's kind of a natural action of GLN on GLN mod B just by left multiplication. But of course, this isn't so interesting to study this orbit because, well, this orbit is everything. There's just a single orbit. And so what you might be interested in instead is thinking about what do B orbits look like inside of this variety. And so if you take T to be the diagonal matrices, then it turns out that B orbits in GLN mod B are parameterized by this group W that is the normalizer of T mod T. And this is actually isomorphic in this particular case to the symmetric group on n letters. So in fact, W is permutation matrices. So what I'm saying is that B orbits are parameterized by permutation matrices, okay? And W is in fact a Coxeter group, and it's usually called the Weyl group of GLN. So then you have this nice decomposition of GLN mod B into this disjoint union of B orbits. And so an individual B orbit is called a Schubert cell, and its closure is the Schubert variety, okay? And this construction that I've just given you, it's much more general. In fact, you can take GLN and you can instead replace GLN by any reductive group. And you can take the upper triangular matrices and you can replace those by a Borel subgroup, and you take the diagonal matrices, replace them with a torus, and then you still have this W that you define as the normalizer of T mod T. And everything that I've just done works out exactly the same. You're interested in thinking about B orbits inside of G mod B now, and these are parameterized by elements of W, and you have this nice decomposition into disjoint B orbits, and you can think about defining Schubert varieties as just the closure of these B orbits, okay? And so then G mod B is just usually called the generalized flag variety, okay? And in fact, almost everything, in fact, maybe everything I'll say in this talk holds more generally in this G mod B setting, but I'll just talk about the GLN mod B setting just for kind of clarity. But pretty much every statement and conjecture that I'm going to make is holds in full generality. Okay, and so these Schubert varieties, they're very well-studied varieties. They have rich combinatorial structure. Many people, including myself, make their living studying these things. But I want to kind of highlight two important properties that are sort of going to be important specifically to this talk. And one of them is that, so these B orbits and thus these Schubert varieties, they're indexed by elements in the Weyl group, which in the type A setting are permutations. So you can talk about a permutation containing certain patterns or avoiding certain patterns. And it turns out that many geometric properties of that Schubert variety are actually characterized by whether the associated permutation avoids certain collections of patterns. So this was first noticed for smoothness, that that Schubert varieties were smooth in type A if and only if they avoided certain patterns. And this was actually generalized to other types. But there are many, many other types of geometric properties that can be characterized by pattern avoidance. For example, whether or not the variety is Gorenstein, whether it's a local complete intersection. Abe and Sarabili have a survey on this where they list, I think, something like 18 different geometric properties that are characterized by pattern avoidance. There's still many open questions. It's a very, very, very well-studied aspect of the subject. And then the other thing that I'll mention that kind of comes up a little bit later is just that the irreducible representations of GLN can be constructed via line bundles on GLN mod B. And this is true actually more generally for the G mod B case. And so this will be kind of important a little later on. Okay, so that's Schubert varieties. And then I want to talk about the other class of combinatorial algebraic varieties, which are spherical varieties. And so the setup here is slightly simpler. So you start off with a connected complex reductive algebraic group. If you like, just think of R being GLN, and then start off with X being an R variety. And so by R variety, I just mean it's a variety on which R acts. So you have an action of R on your variety, okay? And so then we say that X is R spherical if a Borel subgroup in R has a dense orbit in X, okay? So this is a pretty restrictive condition, right? I mean, this is saying like you have a variety and you have an action of this variety, let's say a GLN acts on this variety, right? You would like that you have a dense orbit by the upper triangular matrices, right? And so this is a fairly restrictive condition. So let me just give you a few kind of canonical examples of spherical varieties. So toric varieties, I think, are the maybe the main canonical one you should think about. In particular, if a variety is toric, it's T-spherical. Why is this? Well, what is the Borel inside of T? It's just T. So a variety is T-spherical if it has a dense T orbit. But that's exactly what it means for it to be toric. So this really is, when you're just talking about T, it's really equivalent to it being toric. And so you should think of spherical varieties as being actually a generalization of toric varieties that have at least some of the nice combinatorial structure that toric varieties have. Another two kind of standard examples of spherical varieties is the complete flags. The complete flag variety GLN mod B, this is GLN spherical. Why? Because, well, GLN mod B is a Schubert variety. It is a B orbit closure. So it definitely has a dense B orbit. And the same is true in general for G mod B. G mod B is always a Schubert variety. And so it is always a B orbit closure. So it always has a dense B orbit. So these are kind of like the canonical examples. And these are also very well studied varieties. Dating back, 20, 30 years. They've been classified in terms of combinatorial axioms. And then the other thing I'll just mention is, why do you care in general if a variety is spherical? Well, one of the reasons you care is that it's the same reason you care to know that a variety is toric. Knowing that a variety is toric and knowing the associated combinatorial data can actually allow you to compute various invariants of the variety. And the same is true to a lesser extent, though, for spherical varieties. Okay, so we have these two classes of varieties, Schubert varieties and spherical varieties, and I think a very natural question is the following: when is a Schubert variety a spherical variety? And at this point, well, this question is maybe slightly poorly posed at the moment because of the following. So GLN acts on GLN mod B and it's GLN spherical. That's what I just said on the previous slide, right? We have this action. But in general, GLN does not act on the Schubert variety, right? What I mean by that is you have some point inside your Schubert variety and you look at the GLN orbit. The GLN orbit will take you outside of the Schubert variety, right? Almost always. In fact, always, unless you are actually the flag variety. So to actually make this question even make sense, when is a Schubert variety a spherical variety, you need to say what is your reductive group that's actually acting. And so that's what I want to talk about a little bit now. So parabolic subgroups. A standard parabolic subgroup of GLN is just a subgroup that contains the upper triangular matrices. And it turns out that for each I in bracket n-1, there is an associated standard parabolic subgroup P sub I. And this P sub I decomposes as a semi-direct product of two subgroups, Li and Ui. Li is a reductive group called a Levi, and Ui is the unipotent radical. Now, I don't want to go super into detail about the construction, but at least in type A, in this GLN mod B setting, there's a very nice visualization of these, which is just parabolics are just subgroups that have a staircase of zeros in the bottom left. So for example, if my n is 7 and my I is 1, 3, 5, 6, the parabolic looks like this. So it has those entries always equal to 0, and the other entries can be arbitrary so long as it's actually invertible. Right? So this is what an arbitrary element inside of PI looks like. And what does the decomposition into the Levi and the unipotent look like? Well, the Levi element is actually going to just be the block diagonal stuff. And the unipotent is going to be, well, 1's on the diagonal and these entries above the diagonal. So in fact, what the Levy in this particular case is it's actually GL2 cross GL2 cross GL3 sitting inside of the larger GL7. Okay, and in fact, this will always be true in type A in this GLN mod B setting. Li is always just a product of smaller general linear groups sitting inside of the larger general linear group. And one can give nice descriptions of these Levy subgroups in other types as well, but I'm going to be sticking with type A. Okay, all right, so this is parabolics and levies and, sorry, go ahead. Someone have a question? Oh, okay. So fine. So why am I talking about these levies? Well, they're reductive. Now, when do they actually act on the Schubert variety? Well, so let's recall this definition I had earlier of this left descent set. So this is just these i's such that acting on W on the left decreases the length. And so it turns out that the stabilizer of the Schubert variety XW inside of GLN is actually the parabolic associated to the descent set. So what do I mean by stabilizer? I mean, it's the largest subgroup of GLN that actually acts on this Schubert variety, right? And so it is in fact exactly given by the parabolic associated to the descent set, left descent set. And so what does this mean for us? Well, if you take any I inside of this descent set, then the Levy Li is a subgroup inside of the parabolic Pi, and the parabolic Pi sits inside of this larger parabolic PJW. And in fact, because this PJW acts, that means Pi acts, which means the Levy acts. And so all these levies Li for I in JW, they're just a natural family of reductive groups that act on your Schubert variety. And so I think the properly posed version of the previous question is the following. When is a Schubert variety Li spherical? Because these are a kind of natural choice of reductive groups in which act on our Schubert variety. Okay, so this is the question I'd like to think about now. And maybe before kind of going too much further, I think it's reasonable to ask what is actually known about this question. Is there any sort of previous research on this? And the answer is there's a little bit, but not much. So let me tell you basically everything that's known. So there's a result of Magyar, Weyman, and Zelevinsky, which says, okay, let's not think about any Schubert variety, but just the Schubert variety equal to GLN mod B itself. So they'd say exactly when GLN mod B is Levy spherical. It is Levy spherical if and only if I is one of these three. And let me tell you what the associated Levy is for each of these three. When I is equal to this full set n-1, the associated Li is actually GLN itself. So this is saying GLN mod B is GLN spherical. What is the associated Levy here? The associated Levy here is GL1 cross GLN-1. And the associated Levy here is GLN-1 cross GL1. So the three levies that act spherically are the largest ones. It's GLN itself, the one that's slightly smaller, and the other one that's slightly smaller. So these are the only three levies that have a dense orbit, which intuitively makes a bit of sense, right? You would expect that the largest ones are the ones most likely to have a dense orbit of their upper triangular matrices. So that's this type A result. And then Stembridge in 03 generalized their result from just the type A setting to the general type setting. And what he showed is actually G mod B is Li spherical if and only if I is equal to this, which in the associated Levy here is just G. So this is saying the only Levy that acts spherically on G mod B is G itself, nothing else. So this is it for the flag variety. And so the only other result that I'm aware of is this one due to Karuppuchamy. And his is specifically, so his is for any Schubert variety now, but now we restrict I. And we say I is equal to the empty set. And when I is equal to the empty set, the associated parabolic is actually just B, is just upper triangular matrices. And the Levy inside of B is just the torus. And so what he's done is he shows exactly when a Schubert variety is L empty set spherical, which is when it's toric. So he gives a classification of toric Schubert varieties. And what he says is that the Schubert variety XW in G mod B is L empty set spherical, that is T spherical, that is toric, if and only if each simple reflection appears at most once in any reduced expression of W. And this should look really familiar. This is all very similar to the stuff we were talking about at the beginning of the talk. And I'll make that slightly more explicit in a second. The one other thing that I'll just mention really quickly is that part of the reason I think there's very little data on this is that I don't know of any actual finite algorithm to actually check if an Li is spherical. I know of algorithms that can certify that it's not spherical in a finite amount of time, but I don't know of any algorithm that can certify sphericality in a finite amount of time. And so I think that's that's something else I'm very interested in sort of thinking about.
So, but if you were so basically you're checking if a Borel subgroup Li has a dense orbit.
Yeah, the Borel inside of Li has a dense orbit.
And so if it were enough to check on if you chose it was enough to check at the T-fixed points, for example, obviously that's not enough, but that would be easy to check if you calculate the dimension.
Right. Yes, definitely. Right. So there are some clear necessary conditions, and one of them is definitely a dimension consideration. But yeah, so I definitely know of some necessary, but not. I'm not aware of any sort of sufficient conditions, at least as far as like a finite time algorithm. But yes. Okay. So now I'd like to sort of tie everything together. So we had this Coxeter combinatorics stuff that we were talking about, and now we have this sphericality stuff, and here is the conjecture. So the conjecture is that a Schubert variety is Li spherical, that is there's a dense Borel inside of Li orbit, if and only if W is I spherical, this Coxeter combinatorial definition from the beginning. And I should say this is the type A version of the conjecture, but the conjecture is actually type independent. The conjecture is just XW in G mod B is Li spherical if and only if W is I spherical. Okay, and so I think the very natural first thing you would want to know is, does this work in the cases that are already known? And well, XW is L empty set spherical if and only if W is empty set spherical. This is exactly the contents of the lemma, right? That lemma I had early on was that W is empty set spherical if and only if each simple reflection appears at most once. But that's exactly what the Karuppuchamy result from the previous page says. The Karuppuchamy result says that it's actually geometrically spherical if and only if each simple reflection appears at most once. So our definition of sphericality matches up exactly with the definition of geometric sphericality, or with the geometric sphericality in this case. And this was actually the motivation for the definition in the first place. And then I won't go into these in detail since I'm a little low on time, but I'll just say that we can show that in fact this conjecture holds true specifically in the cases of that Weyman, Magyar, Zelevinsky, and the Stembridge cases. In particular, it is I spherical exactly when it should be according to our definition. But what I want to sort of stress at this point is all three of these theorems that I have listed here are sort of proof by correlation, right? Someone else has shown exactly when these varieties are Li spherical. We show exactly when the associated W's are I spherical, and they exactly match up, and so conjecture holds in those cases. But what you would really like, right, is you would like to say, I start off with the definition of W being I spherical, and I directly prove the geometric sphericality and vice versa, right? And that's definitely not the case for these first three theorems. And so that is the goal of the last third of the talk, is to sort of start building up a framework where you can actually do this, where you can start with the definition of being I spherical and actually show that you get geometric sphericality and vice versa. Okay, and so that's this last section. And so this last section is about Demazure modules and their key polynomials. And well, since I've been hanging out.
Can you hold on for a second? So we have a question.
Sure.
Can you go back a slide?
Can you go back a slide?
Mhm.
So, is it obvious that one direction is easier to prove than the other direction?
Did you hear that, or should I?
So is it obvious if one direction of the conjecture is easier to prove than the other? Is that the question?
Yes.
Okay, yeah, so I don't think either direction is obvious. Like we have a lot of data, heuristic data backing up this, and it works in the cases that we know of, but I don't think either direction. I think, so one direction, the motivation for this I-spherical definition, especially the S2 portion of the definition, is definitely making sure that the dimension of your Schubert variety is not too big with respect to the dimension of your Borel. So there's definitely some sort of geometric intuition baked into this definition that's sort of encapsulating some necessary conditions, but I don't think any of the two directions is obvious.
Okay.
Thank you.
Thanks.
Okay. All right. Yeah, so now I want to talk about Demazure modules and their key polynomials. And well, since I've been spending the last few years hanging out with algebraic combinatorialists, I thought maybe I should really be saying key polynomials and their Demazure modules, but you know, it depends on your point of view. And so just a bit of background here. So I want to first define Schur polynomials. And so a partition of length n is just a sequence of integers that are weakly decreasing, sequence of non-negative integers that are weakly decreasing, and I'll let par n just be the set of such partitions. And so given a partition, you can define the associated Schur polynomial in n variables. It is going to be some summation over all semi-standard tableau of shape lambda with entries in 1 through n. And for each such semi-standard tableau, you get some monomial, and that monomial is raised to the power equal to the content of that tableau. So we'll do an example in a second, but the idea is you get a bunch of monomials that are each indexed by some semi-standard tableau of a particular shape. And then it's not immediately obvious from this definition, but these Schur polynomials are actually symmetric. So they're symmetric polynomials in the variables x1 through xn. And more than that is actually true. If you take all of these Schur polynomials and you index them over all partitions of length n, they actually give you a z-linear basis of sim n, where sim n is the symmetric polynomials in n variables. So given any symmetric polynomial, I can express it as a linear combination of Schur polynomials. And so maybe just a quick example of what I mean by this Schur polynomial definition. So if you let n equal 3 and you take the partition 2, 1, 0, then the associated Schur polynomial is this. And you get one of these monomials for each semi-standard tableau of shape 2, 1. So for example, 1, 1, 2, this here is semi-standard. And since there are two 1s, then the exponent of x1 is 2. And since there's 1, 2, the exponent of 2 is 1. And the exponent of 3 is 0. And x3 is 0 since it appears 0 times. And so for each of these, you get a monomial. And then you'll notice, for example, that this has coefficient 2. This is precisely because there are two semi-standard tableau of the same content, 1, 2, 3, that have the numbers in different places. Okay, so this is some special family of polynomials that give you a basis of the symmetric polynomials. Okay, and so one can now complicate this a little bit, and so I want to talk about split symmetry in algebraic combinatorics. So this is a notion Alex and I introduce in our paper, and so the idea is you take a bunch of integers d1 through dk, and then we define pi d to be the subring of pol n. So pol n is just the ring of polynomials in n variables, x1 through xn. So pi d is the subring consisting of polynomials that are separately symmetric in variables that depend on d. So D gives you some partition of your variables, and I would like my polynomial to be separately symmetric in the different subsets of variables. And so it's not too hard to show that actually pi d is just isomorphic to this tensor product of symmetric polynomials. So this would be like sim d1 is just polynomials symmetric in variables x1 to xd1, and then sim d2 minus d1, these are polynomials symmetric in variables xd1 plus 1 up to xd2, etc. So that is what these pi d's look like. And we say that a polynomial is d split symmetric if it lives inside of this ring. Okay, so these are just polynomials that are not fully symmetric, but they're partially symmetric under some permutations of their variables. And so what's the point of this? Well, the point of this is the following. So now I'm going to take a sequence of partitions. So this lambda superscript 1 up to lambda superscript k, this is going to be a sequence of partitions, right? So their lengths depend on d. This is just a sequence of partitions. And we say that the associated d-Schur polynomial is a product of Schur polynomials. So this is here is the Schur polynomial associated to lambda 1. And it's got some collection of variables. And then this is the Schur polynomial associated to lambda 2 in another set of variables. And so you just take one of these Schur polynomials for each of the lambdas in your sequence, and you take the product of these, and this gives you an associated d-Schur polynomial. And this d-Schur polynomial lives inside of this pi d. And in fact, more than that is true. They give you a z-linear basis of pi d. Okay, so this is a collection of polynomials that give you a z-linear basis of these rings. And this sort of follows immediately by this isomorphism up here, and also the fact that on the previous page that the Schur polynomials give you a z-linear basis of just sim n. Okay, all right, so, right, and so why am I talking about this? So the point of this is the following. I want to talk about multiplicity now. And so there are kind of two really common types of multiplicity problems that show up in algebraic combinatorics. So the first one is you have a polynomial that is symmetric, okay? And you have this symmetric polynomial. What that means, as I said previously, is that you can write it in the basis of Schur polynomials. And we say that this polynomial is multiplicity free if, when you write it in this basis, all the coefficients are 0 and 1. And so this is a very, very, very well-studied problem. Like asking when certain polynomials inside of certain infinite families are multiplicity free is very well studied. Stembridge studied when products of Schur polynomials are multiplicity free. Thomas and Yong studied when skew Schur functions are multiplicity free. Many other people have studied this problem for various other families of problems. I have a recent result with two grad students, Shiliang Gao and Gidon Arelowitz, when skew Schur polynomials are multiplicity free. But this is well studied. This is like a very small subsection of the results on this. And then there's another type of multiplicity free problem that's not as well studied, but is also shows up quite frequently in the literature, which is you have a polynomial, and you can think about writing this polynomial in just the monomial basis. And then in the monomial basis, you can ask whether or not it's multiplicity free. That is, each monomial coefficient is 0 or 1. And so Fink, Meseros, and St. Dizier have a result saying when Schubert polynomials are monomial multiplicity free. And Alex and I have a recent result that's related to these results about when key polynomials are monomial multiplicity free. And so here's kind of the point between this d-Schur definition, which is now take a polynomial that is split symmetric, it's inside of this pi d, then by this fact I have from the previous page, you can write it as a linear combination of these d-Schur polynomials, and you have some coefficients associated to each one. And so you can ask, when is it d-multiplicity free? That is, when are all these coefficients 0 and 1? And the point is, this actually gives you, this is a framework that kind of generalizes these two disparate types of multiplicity free problems, because when d is equal to the empty set, then par d is just partitions. And so pi d is just symmetric polynomials. And so asking if something is d-multiplicity free when d is the empty set is just asking whether something's multiplicity free in this first sense. And when d is equal to this bracket n minus 1, then par d is actually just compositions, and pi d is just actually polynomials. And so asking if something is d-multiplicity free when d is equal to this bracket n minus 1 is just asking, is it monomial multiplicity free? But the point is, now you can kind of interpolate in between these two multiplicity paradigms, right? You have the one multiplicity paradigm, which is when it's symmetric, the other multiplicity paradigm when it's just a polynomial. But now you can sort of ask all these questions in between for various different values of d. And so there's a representation theoretic motivation behind this, but since, again, I'm a little low on time, I'll skip over it. And if anyone's interested at the end of the talk, I would be happy to talk about that. So I'll skip this slide. And so I'm getting close to the end. So I just want to define key polynomials really quick, and then I can kind of tie everything together. And so you start off with a weak composition. This is just a vector of integers that are non-negative. And then you define a Demazure, the Demazure operator. This is an operator that takes you from polynomials to polynomials. It looks like this. It's a little messy, but that's the definition. And then using this operator, you can define key polynomials. So given a weak composition, the key polynomial kappa alpha is, well, it's just equal to this monomial if alpha is weakly decreasing. And if alpha is not weakly decreasing, then you have a recursive definition. Kappa alpha is equal to this Demazure operator of kappa alpha hat, where alpha hat, you've taken two entries in your composition that weren't weakly decreasing and you made them decreasing, or that weren't decreasing and you made them decreasing by swapping them. And so you just keep repeating this over and over and over again. It's a messy recursive definition, but that is the one definition of key polynomials. And there's, of course, things you have to check, right? It's not so clear that this is actually giving you polynomials, but you check that and you see that it works out. And so this gives you your definition of key polynomials. And so what's the point? So here's the point. This is the thing that ties everything together. So now you take some W inside of Sn, so a permutation, that is something that's indexing a Schubert variety, and you look at the, you take some subset I inside of the descent set, the left descent set, and then I'm going to define my D to just be the complement of I. Okay, so this is the data we're starting with, and let lambda just be some partition. So then the point is that these key polynomials, they in fact live inside of pi d. That is, they are split symmetric. They're partially symmetric. And so there are a couple things to say here. First of all, kw lambda. So this w lambda, so lambda is a partition, w is a permutation. So you act on the partition by just permuting it according to the permutation. That gives you some composition, right? So this kw lambda is just the key polynomial for some composition. And I'm claiming that if these things above are true, then in fact, you know that it's living inside of this ring pi d. I think this is something that's previously known. I don't think that this is like special to us realizing this fact, but we couldn't find it written down anywhere. And so we proved this. But here's the point. What you can show is that the Schubert variety XW is Li spherical if and only if kw lambda is d-multiplicity free for all lambda in par n. So you reduce this geometric sphericality question to a question about when certain infinite families of polynomials are all multiplicity free. And there's, again, I can talk about kind of the proof of this if anyone's interested. There's essentially a geometric proof, geometric representation theoretic version of this proof having to do with Demazure modules, because these key polynomials are actually characters of Demazure modules. But the point is, this actually gives you a concrete way of connecting the two, because now you can start off with your I-spherical Coxeter definition, and you can think about how does that affect the multiplicity of these associated key polynomials, and then you can use this theorem to then show things about when the Schubert variety is geometrically spherical. And so to do this, well, you need to be actually able to know how these key polynomials decompose. And so Ross and Yong actually give a positive combinatorial rule for writing these key polynomials in this D-Shore basis. And we use this now to prove our conjecture for certain cases. And so let me tell you about one of those cases. So a descent, so not a left descent, but just a descent of a permutation is if you write your permutation in one line notation, that is just A1, A2 up to AN, a descent is an index J such that AJ is strictly greater than AJ plus 1. And then a permutation is called bi-Grassmannian if both W and W inverse have a unique descent. So for example, this W here has a unique descent from 5 to 1, and its inverse right here has a unique descent also from 5 to 1. So this W equal to 3, 4, 5, 1, 2 is bi-Grassmannian. And so Alex and I used the theorem above to prove our conjecture for bi-Grassmannian Schubert varieties. That is, let W be bi-Grassmannian, then the Schubert variety is LJW spherical if and only if it's JW spherical in the Coxeter sense. And we do this exactly by showing you start off with W being JW spherical. You then show that all of the associated key polynomials are going to be demultiplicity free. And then this theorem says that that will in fact give you that the Schubert variety is geometrically multiplicity free. Okay, so is time's up or is there?
How much more do you have?
So I have one more slide.
Yeah, let's do that.
That should take like 1 or 2 minutes.
That's fine.
Okay, all right. So yeah, let me just wrap up now with this final slide. So I want to talk particularly about this case here. So now we take, again, just W is some permutation, and the following are equivalent. So this 2 and 3 equivalence, that is XW being T spherical, L empty set spherical, this is equivalent to each simple reflection appearing at most once. This is what we've been talking about throughout the talk. And then it turns out that this is actually also equivalent to W avoiding the patterns 321 and 3412. And the proof of 1 and 2, the equivalence of 1 and 2 is essentially this Karuppuchamy result. And the equivalence of 2 and 3 is proved by Bridget Tenner, and it's actually not, there's no geometry involved whatsoever. She was just interested in looking at the sort of combinatorics of reduced words. And so what Alex and I do in a subsequent paper is we prove the following. We prove that the key polynomial kappa alpha is n-1 multiplicity free, which is monomial multiplicity free, if and only if alpha avoids the following 5 patterns. And so this actually allows us to prove directly the equivalence of 1 and 3. And the reason I bring this up is there's quite a lot of literature regarding these types of orbit problems, not just about sphericality, but literature involving these like orbit problems that's sort of studied from an algebraic groups perspective. And then there's a lot of literature studying just sort of properties of like reduced word combinatorics just in general. And I think that the thing that makes me most excited about this project is I think it offers sort of a bridge between these two types of problems. Sort of, it says, you know, if you're interested in thinking about, say, reduced word combinatorics, or if you're interested in thinking about orbits, there is actually a way via representation theory and algebraic combinatorics to connect these and to think about these problems from a different perspective. And so I think that that's sort of, for me at least, one of the most exciting things about this project has sort of been sort of thinking about how you can translate problems in these two different realms to one another. Okay, and so I think I'll finish with that.
Okay, thank you very much. Any questions?
Can you go back to this previous slide? Yeah, so I mean, is this, so in terms of this Li spherical, so is that because somehow the KW lambdas determine, the kappa W lambdas determine the decomposition of the, you know, the section, all the sections of the line bundles on that Schubert variety basically?
Yes. So here's the connection essentially. So there's a number of equivalent definitions of sphericality. And one of the equivalent definitions of sphericality is that if you look at the space of sections of any, so let's say, okay, a variety is G spherical. It's equivalent to, if you look at the space of sections of any G linearized line bundle, that they should be multiplicity free.
Is it any line? No, is it any line bundle? You need the section of all the line bundles together.
So it's individually, I think. It's that each specific section of each space of sections. So it's like this H0, XW, L lambda should be G multiplicity free for any L lambda that is G linearized. And so the point is, right, in type A, these are Demazure modules. And the characters of these Demazure modules are these key polynomials or Demazure characters. And so if you're interested in checking whether this space of sections is G multiplicity free, then that's equivalent to checking by character theory, checking whether the character is multiplicity free.
What is special to type A about this?
I mean, so there's nothing special in type A in the sense that this works in general. It's just you have a little bit less, the characters are a little bit less well understood in other types. Like for example, this positive combinatorial rule for finding the coefficients in the expansion, this is for type A specifically. But of course, actually the above is true in general. This theorem is true in general if you state it slightly more generally. What you'd say is that XW is Li spherical if and only if the characters of the Demazure modules are all multiplicity free in that type, in that specific type. So it would just be some other polynomial that's the character. You would be checking whether or not that's multiplicity free.
All right, I just want to follow up on this. So when you mean demultiplicity free or D-sure polynomials, can you give me the, I know what the interpretation of the sure polynomial. Can you give me the interpretation of the D-sure polynomial?
Sure. Yeah, so that was actually what I sort of skipped, the sort of representation theoretic motivation behind this. So right, the irreducible representations of GLN are indexed by partitions. And so given a partition, let's denote the associated representation just by S lambda. And so the character of S lambda is just the Schur polynomial, right? So that is the relationship for just Schur polynomials and irreducible representations of GLN. And so here's the idea is that, well, what do the irreducible representations of Levi subgroups look like? Well, if you remember, these Levis are products of smaller GLs. So in fact, they should just be tensor products of irreducible GL representations. So in particular, you can index the irreducible Levi representations by sequences of partitions. So given a sequence of partitions, you have an associated representation S lambda 1 lambda b, this is just equal to S lambda 1 tensor, S lambda 2 tensor, etc. And these have character that are exactly these D-Schur polynomials.
So it's just the algebra tensor product.
Yes, just the normal tensor product. So right, so these are just tensor products of the GL's factors. And so that's exactly why the character here is just a product of the characters of the GL reps. And so, right then, writing some L character in this D-Schur basis is exactly writing the decomposition of the L module into a sum of irreducible L modules.
Okay, any other questions?
Oh.
Okay, one more
So
question.
this, so can you generalize this to characteristic P?
Yeah, so I mean, I think that's definitely one possible future direction, but I have to say that sphericality is sort of much more complicated there. I mean, well, obviously everything's more complicated there, but I think that kind of there are many more, there's lots of problems that maybe need to be solved first before this type of question would be at all tackleable in sort of characteristic P. But certainly it all makes sense. You can certainly like ask the same questions for sure. But I have to say I haven't thought too much about it since we're still working on proving the characteristic zero version completely. So because essentially we've proved the conjecture in certain cases, but we haven't proved it even in general type yet.
When isn't the most interesting case when I is actually the AW itself? That's the biggest sort of act. I mean, I guess you need to see if there's a smaller I, but is it more tractable if I is make like make I as big as possible? I think that's the most symmetry you have.
Yes, yes. I mean, so right, exactly. I mean, this is kind of one case that you would like to prove probably first, is sort of restrict your case to when I is actually the full left descent set, and then try and see whether it holds in that case. Although a lot of the tools that you end up having actually just work in general for any I. It's not too restrictive to just think about a general I, but certainly that is one way you could consider tackling this, is just sort of work with the largest. In fact, I think the one thing that is definitely true is if you're interested in giving pattern avoidance criterion, I think those probably only exist if you're willing to restrict yourself to just thinking about the largest. So you can say something like XW will be LJW spherical if and only if W avoids some patterns. Like, I think that that's sort of a reasonable thing to attempt to do, but yeah.
Do you have other, so you have the condition about sphericality is kind of complicated. Do you have more data I mean, it seems like there's only a relatively small number of cases where it's actually true. So do you have more data that would tell you that this is really the right condition?
Yeah, so I mean, so for example, this theorem gives you a pretty good way of testing this in type A at the very least, right? By this theorem, because we can actually compute these decompositions, and so we can check when this key polynomial is demultiplicity free. Obviously not for all lambda, but we can check it for many lambda. And so we've checked, I think, up to like S8 or S9, for example, and this condition works exactly on the nose as in that sense. And then similarly, if one is a bit careful, you can do using this same type of idea in other types, you can test them as well. And so we've tested small examples in just about, I think every other type, and this works for small examples as well in other types.
Okay, good.
Okay, any more questions? Okay, so does not seem to be the case. So yeah, let's thank Reuven again.
Thank you. Nice talk.
Thank you.